Okay, let's continue with the exercise. You have the exercise on, you can download them from Teams. Those are direct application on RSA and Diffie-Hellman. Okay, so the first one is we want to perform the encryption and the decryption using RSA algorithm. Okay, and for the following value of P equal 3, Q equal 11, which are the P and Q prime number, and the public key equals 7, and the plain text M that we want to encrypt is equal to 5. So this is the simple application. You can check the uh, slides. So if we have, let's say, P equal 3, Q equal 11. So in this case, we have to find N equal P times Q, which equals 3 times 11 equals 33. And we want to calculate the phi function, which is P minus 1, Q minus 1. And if we want to encrypt here, it's very easy because we have N. So the encryption in this case will be the encryption ciphertext equal M to power E mod N, which is equal 5 to power 7 mod 33, and in this case 5 to power 7 mod 33. uh, uh, we can find the ciphertext. It's equal to 14. Yes. Okay. And if you want to apply the method we use them, it's possible to write 5 to power 7 is 5 to power 4 times 5 to power 2 times 5. So here it's 5. The remainder is 5 mod 32. Here is 25 mod 32. And here if we want to use uh, uh, 5 to power 4, it will be 31. And after that, we multiply them and we find the result. It will be 40. So this is for the encryption. So for the decryption, we need to find the secret key, which is D. So that's that we should find phi of n. In our case, phi of n equal p minus 1, 2 times q minus 1, 10 is equal 20. And we should find D such that typically D will be prime also with y with e, and such that, as we said, D times e should be equal 1 mod 20. So in this case, it should be equal 1 mod 20. In this case, we should find in this case D times 7 equal 1 mod 20. This means that D times 7 equal K times 20 plus 1. Okay, so if you want to calculate this, for example, for K equal 1, for K equal 1, for K equal 1, so this means that for K equal 0, it will not be okay. For K equal 1, it will be 21. So D in this case is equal 3. It's possible so to have for k equal 1. So the decryption key is equal 3. And in this case, the private key will be 3 and n. So the public key is 7. The public key is 7n, which is 33. And the private key is 3 and 33. In order to decrypt this message, simply you should write that m equal 14 to power 3 mod 33, and you can verify that it will be equal to 5. Okay, so this is for the first exercise. Okay, the second exercise, here you intercept. You know that the system is working with RSA, and you intercept the ciphertext C equal 9. And you know that the public key equal 3 and n equal 33. What's the plain text? So here you want to do the brute force attack over RSA, which is factoring the problem. It's a kind of factoring problem. Remember this in the course. So you have n equal 33 and n equal p times q equal 33. So you will try to find what are the two prime number, such that if you multiply those prime number, okay, in this case you obtain the value. This is a way to do. So typically you will try to do this. Okay, so if you try, you say, okay, let's say the different combination, what are the prime number that to reach 33? We have 1, 2, 3, 4 no, 5 it's also a prime, 6 no, 7, 8 no, 9 no, 10 no, 11, 12, 13, 14, 17, 19, 23, and so on. So you just need to reach up to the half, for example, because if you want to find two terms, so in this case we can find that 3 times 11, okay, are the two prime number that if we multiply them, we can obtain them. This is the factoring problem. So we identify that one is equal to 3 and the other one is equal to 11. So in this case, we can deduce the phi function, which is p minus 1 q minus 1, 2 times 10 equal 20. And this case, because we know the public key is equal to 3, we should find d times 3 will be equal to 1 modulo 20. We already did it in exercise 1. It was it's the inverse. So in this case, we should find that d times 3 equal k times 20 plus 1. Okay, and we can find that d equals 7. And in this case, in order to decipher, so the plain text m is equal 9 to power 7 mod 33. And if we want to do the calculation, it will be equal to 15. Okay. And if you want to verify, you should just make that 15 to power 3 mod 33, it will be equal to 9. Okay. So because we did two examples, I want to ask you to do by yourself the third exercise, which is also you intercept a text, a ciphertext C equals 61, and you have here a public key E equal 11 and the N equal 91. So try to do the factoring and to see what could be P and Q and how you can also deduce the private key and you can decrypt the ciphertext. Okay. So let's move to exercise 4. In exercise 4, we have an RSA crypto system. Okay, and this RSA crypto system. We have the following parameter: E equal 23, N equal P times Q, just to facilitate. And here we want to encrypt the message. It's very easy. Here we have to calculate ciphertext equal the plain text to power 23 mod n. In this case, n it's equal 233 times 241 is equal 56,153. So it's equal. So because we have, let's apply multiply and square method. It's very easy here. If you remember that E here is equal 23, remember 23 can be written as 23, it's 16 plus 4 plus 2 plus 1. So this means that it's 1, 0, 1, 1, 1. Okay, 8 is not here, it's space 2. So remember that the idea was to start with a function f equal 1. And for e equal 1, it will be 2. For this one, it will be f times f. So 1 to power f square times 2, it will be 1 square times 2, it will be equal to. Okay, because so f now equal to, because here is 0, we will not multiply by 2, it will be just f squared, so it will be 4. Here, because it's 1, it will be f square times 2, f square. So 4 square times 2, 16 times 2, it will be 32. Because it's 1, we should multiply by 2. So 32 square times 2, which will be 32 square is 1,024 times 2, it will be 2,048. And here the last one, it will be 2,048 square times 2. 2,048 square times 2, it will be equal to I didn't calculate it, but because we need it modulo n, so we should find it with modulo n, huh? Okay, because remember that in the equation we are working always modulo n. Okay? So this will be the encryption of this value. Okay, this is the encryption of this value. So now, if we want to continue and to encrypt the message, because the message is 2 here, okay, that's why I multiply by 2, huh? That's why I multiply by 2. Okay. So the result here will be the encrypted, the encryption message of. Here, as part B, we should compute the private key corresponding to the given public key. Here, because we have P and Q, so we have phi of n equal P minus 1 Q minus 1, and it will be 232 times 240, and we should find D times E to be equal 1 mod. Let's multiply this, it will be 55680, 55680. So in this case, E is equal to 23, so D times 23 is equal K times 55680 plus 1. Okay, this is the way. So typically D is the integer number equal 55. I can, okay, 55680 plus 1 over 23. We should take the different value. So for k equals 0, it's not okay. For k equal 1, it's not okay. Until, for example, for k equal 8, we find that this will give an integer. and D in this case equal 19, 319, okay, 1,367. Okay, you can try it also. It's okay. And now you can decrypt because you have this decryption. You can decrypt and verify to obtain the value of 2. Okay. For exercise 5, you have Diffie-Hellman. It's very easy. You have the generator and you have N and you have X and you have Y. Suppose that Alice and Bob choose the private number. Alice choose 6 and Bob choose 10. And the generator G is 2. What will be the public and the private key? It's also a simple example where we have here in this case N equal 19 and the generator or alpha or the generator is equal to 2. So Alice will calculate, Alice select 6. So Alice will calculate 2 to power 6 mod 19. It will be equal 7 and send it to Bob. Bob will calculate 2 to power 10 because the private of power is 10 mod 19. It will be equal to 17 and send it to Alice. So each of them will calculate. So it will be Alice will then calculate 7. Alice will receive 17. So Alice will calculate 17 to power 6. And Bob will calculate 7 to power 10. All are mod and mod 19. Mod 19. Both will have the same secret key, which is 7. Okay, so this is the way to apply it. So the public key are here 7 and 17. Okay, for Alice is 7 and for Bob is 17. The private key of Alice is 6. The private key of Bob is 10. And the secret key, the exchanged secret key is 7. Is the Diffie-Hellman protocol vulnerable against amendment attack? Yes, we already investigated this during the course, and you can explain and you can justify how Darth could attack both. Okay. The last exercise is related to the chosen ciphertext attack here. Here we illustrate a simple application of chosen ciphertext attack. Bob intercept the ciphertext C intended for Alice and encrypted with the Alice public key E. And Bob also want to obtain the original message, which is C to power D mod n. Bob choose a random value R less than n and compute R to power E. And after that, he multiply Z times C. Remember that in our case, we in the course, I presented you the case where R equal 2, multiple of n. Okay, so in this case, X equal Z times C modulo n, and then T equal R minus 1. So next, Bob gets Alice to authenticate sign to sign X. It's a kind of track to say that sign me this to verify. So in this case, Alice will sign this X with her private key and then decrypting X. So in this case, Alice will return Y, which is equal X to power D mod n. So how Bob used this information to find M? This is what we call chosen ciphertext attack. It's a well-known attack. Okay, it's here we can assume here that's really a kind of attack against RSA. So in this case, because Z equal R2 times E, yes, modulo n. Okay, and R in this case, okay, here, when receiving X, Bob will compute T times Y. Okay? And in this case, T times Y mod n will be T is R minus 1 and Y is XT mod n. Remember that R minus 1 in our case and X in our case is R minus 1 Z to power D C to power D mod n. Yes? And Z to power D is Z itself is R minus 1 R and it's C power D, because here Z is RE, okay, and then Z is R E to power D. E to power D is equal to 1 modulo n. So R minus 1 R is 1. We obtain C to power D modulo n, which is M. C to power D modulo n is n. So that's why when receiving Y, Bob just will calculate Y times T. Okay, and he will obtain modulo n and he will obtain M. Okay, and remember that in our case, when we used R equal 2, we say that we obtain 2M. So the objective is to multiply by 2 minus 1. Here it's T equal R minus 1, which means that T equal to minus 1 mod n. Okay, so this is the simple chosen ciphertext attack. It's presented here as an exercise, and in the course we presented the case where R equal 2. Okay, this is an attack against RSA. And also please consider that the example we presented in the course for the Chinese remainder theorem, it could also be done as an exercise. Okay, so if you have more question, you can send me or you can ask me in the next session. Okay, so I would like to ask you really to review all those mechanisms and those systems, because we will start in the next chapter to see the hash functions and the digital signatures. Okay.